Welcome to iLecture Online, and here's another example of how you work with problems dealing with the electric field. And the problem looks very similar to one I just did. It says here that we have a 12 microcoulomb charge that is placed at the origin and a second minus 8 microcoulomb charge that is placed 1 meter to the right of the first charge. And now the question says, at what location will the electric field equal 0? So it's a little bit different angle on this type of problem. So again, to get a feel of where to go with this, let's make a diagram. Sometimes you read a problem like this and you go, wow, where do I even start? What do I do? And if you're in a panic and you don't really know where to go, the first thing always is make a little diagram to do like a pictorial of the problem. So let's draw an XY axis. There's your x-axis, there's your y-axis. I drew a short little y-axis because I know everything's going to be on the x-axis. Let's draw our charges. Here's our first charge. It's a positive charge, Q1, and that's equal to 12 microcoulombs. And let's say 1 meter to the right. Over here is a negative charge, and that's Q2, which is equal to minus 8 microcoulombs. All right. Now we try to figure out where we need to go from here. So we're looking for a location where the electric field will be 0, which in other words, knowing that this is a positive charge and this is a negative charge, the electric fields caused by each one of them will be in a different direction, so they will cancel each other out, and we want to find a place where they will cancel each other out in such a way that the result will be 0. So let's imagine here that there's 3 regions. There is region number 1 to the left of both charges. There is region number 2, which is between the 2 charges, and then there's region number 3, which is to the right of both charges. And I would assume that probably in only one of the 3 regions, the electric fields could cancel out to the point where it could be equal to 0. So let's try to figure that out. So I'm going to pick an arbitrary point, or I don't even have to pick an arbitrary point. What I can imagine here is what would the electric field direction be over here for both charges, over here for both charges, and over there for both charges. So let's draw that. So if I'm to the right of both charges, what would be the electric field direction for Q1, or due to Q1? And since that's a positive charge, realizing that the electric field emanates away from the positive charge in all directions, and I'll use different colors for both charges, we can see that to the right here, the electric field will be in this direction, due to E1. Between the 2 charges, it will be to the right, due to E1, or E1, the strength of E1 would be due, of course, to Q1. And then to the left here, the electric field would be to the left here, also due to Q1. All right, so E1 would be to the left in region 1, it would be to the right in region 2, it would be to the right in region 3. So now let me grab a different color. And now let's see what the direction of the electric field would be due to the second charge. And again, remember that for a negative charge, the direction of the electric field is towards the negative charge, like that. So what would be the direction of the electric field over here? And we can see that it would be in this direction. That would be due to E2. What would be the direction of the electric field over here? Well, it would be to the right. And what would be the direction of the electric field over here? Well, that would also be to the right. Okay, now I'm looking for the place where the electric field would be 0. And of course, between the 2 charges, that doesn't look possible because they are not canceling each other out. The 2 electric fields are in the same direction. So this region cannot be the location where the electric field is 0. Now it does look like it's possible over here because the 2 electric fields are in the opposite directions, and over here the 2 electric fields are in the opposite directions. Now here we have to use a little bit of logic here. Let's take the region to the left. Even though they are in opposite directions, the 2 electric fields due to the 2 charges, we are closer to the bigger charge over here, and we're farther away from the smaller charge over here. Which means that no matter where we are to the left of the 2 charges, E1 will always be much bigger than E2, regardless of where I'm at to the left of the 2 charges. the smaller charge being farther away could never cancel out the bigger charge being closer. So this region is also not a good candidate for finding the point where the electric field is zero, which leads us to the region over here, region number 3. Here you can say that since this is a bigger charge, but we're farther away, it is possible that that will cancel out to the smaller charge being closer. We just need to know where that's going to be. And I think we've at least gotten a little bit closer, and so let's just pick an arbitrary point saying over here at some distance x away from the origin, we're going to find a place where the two electric fields cancel out, and therefore the net electric field will be equal to 0. So hopefully that at least puts into a better light for us to figure out how to go about doing it. Now, if we find the right location, that means that the magnitude of E1 has to equal the magnitude of E2. A better way of writing it maybe is to say the magnitude of E1, like that, must equal the magnitude of E2. Now, that means exactly the same thing, but when you write it like this, again, you use absolute value symbols, and then you realize that the sign or the direction doesn't really matter. We're just looking for the magnitude of those two quantities. All right, so let's now calculate E1 and E2, picking an arbitrary location, a distance x away from the origin. So I can say that E1, which is equal to k times Q1 divided by R1 squared, again using the equation associated with finding the electric field due to a point charge. And now when we plug in the values for k, we have 9 times 10 to the 9th newtons meters squared per coulomb squared times Q1. Q1 would be 12 microcoulombs, or 12 times 10 to the minus 6 coulombs, and divided by the distance squared. Now the distance from charge 1 to location that we're trying to find, we call that x, so this is going to be x squared. And that's the magnitude of E1 at this location. So E1 is the magnitude of the electric field due to Q1. We do the very same thing for Q2. We say E2 is equal to K times Q2 divided by R2 squared. R2 again is the distance from the second charge to the location here, which would be this distance right here. And so that would be equal to 9 times 10 to the 9th newtons meters squared per coulomb squared. Multiply that times the charge, and again, we only care about the magnitude, not the direction, not the sign. So this is going to be 8 times 10 to the minus 6 coulombs, and the whole thing divided by the distance. Now, how far is it between these two locations? Well, we know that this distance is x, and distance is 1 meter, so x minus 1 meter is the distance between those two, and so that would be x minus 1 quantity squared. So now I have the magnitudes of E1 and E2, and I know that if I pick the right location, the right x, that those two have to be equal to each other so they can cancel out. So the next step then would be to set the two equal to each other. So we have E1 is going to be set equal to E2, and for simplicity, we're going to leave off the units, because here we're just simply looking for x, and the units are the same for both. So we can say that's equal to 9 times 10 to the 9th multiplied times 12 times 10 to the minus 6, all divided by x squared, equals 9 times 10 to the 9th times 8 times 10 to the minus 6, all divided by x minus 1 squared. All right, so now it becomes an exercise in algebra. We need to solve this equation for x. It's a quadratic equation. Before we get started, though, it looks like we simplify some things. We can divide both sides of the equation by 9 times 10 to the 9th, so that cancels out here. And we can divide both sides by 10 to the minus 6, so we can get rid of this. And we get rid of this. So now rewriting the equation in a more simple form, we could write 12 over x squared is equal to 8 over x minus 1 squared. Now that looks a lot better. We can now cross multiply 12 times this and 8 times this, so we get 12 times x minus 1 quantity squared equals 8x squared. Now, Multiplying x minus 1 by itself, we have 12 times x squared minus 2x plus 1 equals 8x squared. And getting rid of the parentheses, we get 12x squared minus 24x plus 12 equals 8x squared. And then we can subtract an 8x squared from both sides. So we have 4x squared minus 24x plus 12 equals 0. And now, of course, we have a standard form of the quadratic equation that we can solve for x. Maybe before we go any further, let's divide both sides by 4. And then when we do that, we get x squared minus 24 divided by 4 is 6x. 12 divided by 4 is 3, equal to 0. And with a bit of luck, we can actually factor that. Let's see if we can. Nope, we can't. So we have to use the quadratic formula to solve that. So we have x is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Of course, realizing that a, b, and c are the coefficients of the three terms here, a, b, and c. Plugging in the numbers, we get x is equal to minus b, which is a minus times a minus 6, which is 6, plus or minus the square root of b squared, which is 36, minus 4 times a, which is 1, times c, which is 3, all divided by 2a, which is 2. Simplifying this a little bit. And of course, you don't have to do this like this. You can actually put those in your calculator, but I like to simplify things as much as possible. So 36 minus 12, that's 24. So 6 plus or minus the square root of 24 divided by 2. Now realizing that the square root of 24, let's see here, we have a plus or minus. Let's write it like this. So x can equal 6 plus the square root of 24 divided by 2. Or, if I take the negative answer, we have x is equal to 6 minus the square root of 24, all divided by 2. All right. Let's now grab our calculator. And we take the 24, take the square root of that, and we subtract that or add it to 6. So plus 6. And we divide that by 2. And the first answer we get is x is equal to 5.45. And of course, that would be in terms of meters because we plugged in meters in our equation here. And doing the other possibility, 24, take the square root of that, subtract that, make that minus, subtract that from 6 equals, and divided by 2. And that gives us x is equal to 0.55 meters. All right, we seem to have two possible answers. Let's see here. X equals 0.55 meters. Well, that would put us right here. And that is not a possibility because we already realized that the electric fields point in the same direction there, so they cannot cancel each other out. And of course, that comes from the fact that I use a positive 8 times 10 to the minus 6 microcoulomb charge, even though it's a negative charge, because we only care about magnitudes. So logic dictates that this is not a possible answer, which leaves us only with this answer right here, x equals 5.45 meters, which places it kind of over this direction. So if x, so let's put it over here, if x is equal to 5.45 meters, we can then see that the two electric fields will cancel each other out, and at that point, E total is equal to 0. And that's how you do a problem like that. Okay. Let me try to come up with some more examples for you.